Hello everyone, welcome to lecture week 9. In this lecture, we're going to talk about a few things. One is the curve sketching and derivatives, using the derivatives, including the first derivative and second derivative. We're also going to talk about finding the local minimum, how to use the derivative to find the local optimum, and also using derivatives in optimization. Okay, so now let's dive in. So there's so this is the portion about graphing strategies. Now, essentially, it revolves around finding the interesting and helpful points for us to use. So we divide the interesting points at different levels. At the first row level, we have the original function f of x. Now, the interesting points, that would be the intercepts, right? So the intercepts, and those needs to be within the domain. So we also need to figure out what is the domain of the function itself. So we have intercept for x-intercepts, and also y-intercepts. And of course, when it comes to x-intercepts, then it is this equation that will solve for x. And for the y-intercept, we just make x equal to 0. Secondly, we look at the first derivative of the function, which is f prime of x. Now, we want to look at the partition numbers of f prime. So what is the partition number? The partition number is the number that makes the f prime equal to 0, right? And in this case, so these points are also called the critical numbers of the original function f. So this is why we use the sign charts to determine the intervals, whether the function is increasing or decreasing. And then with this, we can also find the local maximum and local maxima and minima. Now we continue to analyze the second derivative of the function. So again, a similar procedure. We construct a sign chart for the second derivative function, f double prime, determine the intervals which the graph is concave or convex, right? In other words, whether it's concave upwards or concave downwards, right? Concave upwards or concave downwards. This is the property determined by the second derivative. And then this will give us the inflection points when the second derivative is equal to 0. All right, and then we can sketch the graph. So this is where we sketch the graph based on the points we have obtained so far, which are the intercepts, the local maxima and minimum, and the inflection points. And we will do this step by step. So with this, we can complete the sketch of the graph, and also we can verify using additional points just to complete the sketching. All right, so now let's look at one example. So we have this function, which is x to the power of 4 and minus 2 multiply x to the power of 3. All right, so let's continue the procedure. So obviously this is a polynomial function. So when it is a polynomial function, then the domain is actually the whole real line, right? So the domain would be negative infinity to positive infinity, right? And for the raw function, so this is where we want to look at. We are looking at the raw function itself, and want to look at the x-intercept. So x-intercept would be the points that's actually making this function equal to 0, right? So setting x to the power of 4 minus this term equal to 0, and this gives us, so if I extract this term out to 0, that gives me x equal to 0 and 2. So both are valid points. And correspondingly, I have the y-intercept, which can be setting x equal to 0, and y is also equal to 0, right? So these are the 2 points. Now, so of course, when x is going to, so I have 2 points here, x 0, and f is x equal to 2, also making it 0. And then this point gives me 0 and 0, right? So what I'm trying to do is to find the intercept of the function with the two axes, right? So let me graph it here so that we build a graph step by step. So this is my x, this is my f of x. So I have two intercepts. First one, and the second one. So this is 1, this is 2. 1, 2. So 2 is also the intercept points. We have 2 points here. So which means the function will pass through these 2 points, right? Now let's look at, so this is f of x. Now let's look at f prime of x, the first derivative. So this will give us 4x cube minus 6x squared, right? So now when setting this to 0, set this to 0, gives us an equation that gives me a solution, right? So let me just express in other ways so that it's clear to get the solution, right? So we just extract the factor, and this gives me x will be equal to 0 or 3/2, right? So these 2 points are called the partition points for f of x, and also the critical numbers, right? Critical points for f of x, right? So at this stage, we can start to use the sign chart method. So this is our x, and we have 2 points here, 0.1 and 0.2, right? 2 points. Let's see what happens now. So we have 0, we have 3/2, right? And we want to look at what's happening, like what is the sign in each interval, right? So this is where we can construct test numbers for x and f of x, right? So the first region 1, let's plug in, for example, -1. So the f of x will be -1, plugin will be negative, let me see, -4 minus 6 be equal to -10, which is negative. So it's going to be negative. So this means it's going to be negative in this region. The second region, let's just plug in 1. So we're just plugging an easy number to work with. So it's going to be 4 minus 6 equal to -2, which is also negative. So the function is also continuing to decrease, right? So it's still decreasing. And the third number, let's plug in the number 2, right? So we plug in number 2. This gives me 4 times 8 minus 6 times 4, which will be positive number, right? So this can be positive in the third region. So what happens is that now we know that the function is decreasing. That's the function decreasing from -infinity to 3/2, right? So it's decreasing. F of x is decreasing, and from this region onwards, maybe let's add the parentheses. So that includes the 3/2. Now this region, f of x is increasing, right? So it's increasing, and we have these points where 3/2 is our local minimum, right? Minimum. Why do I know it is local minimum? Because now it's first decreasing and then increasing. So it's a minimum points, local minima, right? So this is what we know about this function itself. So which means that's 3/2, right? This point 3/2, which is this one. This is 3/2. This point is the point where the function starts to increase, right? So first it's going to be decreasing, and then it's going to be increasing. So this is also another interesting point, and we would like to know what is the value of this function when x equal to 3/2. So plugging in, we have a value which is 27/16, right? So this is negative 27/16. So let's just plot this point out. Right, so this is another point which the function passes through, but it's also a point that the function will be minimum in terms of value, right? And we have this point to this point, so we can actually start to draw a line here because we know that the function needs to pass through this point, right? So pass through this point, and also continues to increase. So continues to increase, right? So at least for this region, we know that the function is actually continuing to increase, and this is what the function looks like. And also in this region, I know that the function should be always decreasing, right? So on the left of the region. So let me just draw a dotted line here. So that's to differentiate. So want to figure out what is happening on the left region because the function still needs to pass through. Let me just draw a sample line. So it could be something like this, right? It could be something like this because the function needs to pass through these 2 points, and also there's this minimum point here. So this is our candidates, but we are not finished yet. So we need to look at the another level of the function, which is the second derivative, right? So let me just take the second derivative, which gives me 12 multiply x to the power of 2 minus 12x, right? So we can set this to 0, and then this gives me, so this, let me just extract the common factor out, and then we have 0 or 1, right? 2 points, 0 or 1. So what does this mean? So these 2 points are the partition points for f of double prime x, right? And we can again use the sign charts 0 and 1 to give us some information. So now this is again x. This is what we are looking at. This is f of double prime. And by the way, this is f of single prime, right? The first derivative. Now again, let's use the test numbers. So we have x. So this is test numbers. We have x. We have f of x. All right, so we need to plug in 3 numbers to determine the sign of the function. So -1, the function, the second derivative will be -1, -12, multiply -2 will be 24, which is positive. So in this region, it's going to be positive, right? So secondly, we need to choose a number in between 0 and 1. So let me choose 1 over 2. And it happens that this gives me -3. So this is negative. And then plug in 2. So plug in 2 gives me 24. So also positive. That is positive, right? So what this means that the function is actually, so if it's positive, right? If it's positive, then it's going to be convex or concave upward, right? It's going to be like this. So this is convex. This is what the function looks like. And then negative will be something like this, concave downward, and then again concave upward, right? So meaning this point is my candidate. So I have 2 inflection points. So this is the first point, this is the second point, and both points give me the case when the second derivative is 0, right? So let me just find the point, the coordinate of this point. So I have 1, which is 0, and then plug in gives me 0, right? And then the second point, which is the derivative of 1, -1, and y will be -1. So meaning these are the 2 points that actually the function is the second derivative is 0, and these the inflection points, meaning there will be a change of concavity, right? Change of concavity. So 0 and 0 and 1 and -1. So let me just map this out. So this is 1, and this is -1, right? So -1. So this is the second point. Now, so what is happening is that now before, so this is 1 point, this is second point. Okay, so this is the first point when we look at this point. So before this point, the function is actually concave upwards, right? So this concave upwards. So we need to draw something like this. So let me just erase this so that's can say this is concave, right? So concave upwards. So and after this point, there's an inflection happening. So this is gonna be an inflection point, and my line is gonna be something like this. So it's gonna be downwards, right? Concave downwards, and then again passes through this point. So I'm still decreasing. The function is still decreasing because of the first derivative is going to be negative, right? But I'm actually having an inflection point. So this is my second inflection point. Then I'm going to change the concavity to something like this. Let me redraw to something like this. So it's going to be concave upward. And then we have it here. So and this is my function. And we have for the rest of the region, which is above 1, and it's all concave upwards. Right? So this is how we can draw the function. And we can actually plug in additional numbers to verify, to test. So this is the illustration of the drawing out the function using the raw function intercept. So they will have intercept, the first derivative set to 0, give us the sign of the function, whether it's increasing or decreasing. The second derivative, which gives us the concavity of the function. And we have, so after we know about these few characteristics, then we can have a better idea how to draw the function itself. All right, so let's look at a few other concepts. So now, first one is the intercept. So the increments. So increment basically allows us to study the numerator and the denominator of a difference quotient separately, right? Separately. So it is the definition is very straightforward, right? We basically take the different y's and then take the difference, and then we have the difference in y. So this represents, so this delta y represents the change in y corresponding to a change in x, right? So first we have a change in x, then we have corresponding change in y, and then both points are evaluated. So this point 1, point 2, these both points are evaluated. That's the different, that's the same curve, right? So this is curve f of x. Now, we can actually make a connection by taking the same difference quotients, right? So we have 2 points, and then by adding these limits, now this gives us the definition of a derivative, and we can use different expressions to express the same thing, right? So, so now here we have 2 examples. Now we can just plug in the definition of the function, and then to get the expression for the different increments. Now, increments is related to differentials, right? Differentials is now we are using derivative to express the differential. So what is a differential? Differential we express as dy. So d stands for differential, right? And it's basically can be calculated using this. So what is this? So we know that if the derivative is going to be dy over dx, right? You can just multiply dx to get this expression here. So basically, dy stands for the change in y using the derivative or using the tangent line to approximate the change in y. So we'll talk about more about the approximation later. So this is again how we can express the differential in y. Now, so okay, so we have it here. So the approximation, essentially, we're approximating delta in y, right? The change in y using the differential in y. So this is using the difference quotient, right? So this way to approximate the. So basically we have 2 terms here, and both can be approximated using each other. So now to calculate this, basically we can plug in the formula, which is here, calculate the derivative, then get a change in x, which is dx, right? This is most of the time is given, and sometimes, so this actually represents how much is how detailed, right, is the approximation. So then we have the calculate the dy based on the expression above. Now, we can compare the approximation in terms of how good it is, right? So if you look at this graph here, this graph gives us 2 points. Again, so points 1, point 2. And if you look at the vertical distance, which is the delta y, so this is the true distance between these 2 points in terms of the y-axis, right? The value, the change or the difference in the y value. And we can also draw another dy, which is the differential in y. So this dy actually is calculated by taking these dots and then drawing a tangent line across these points, right? So this is the tangent line. And we have covered earlier, we can guess the equation of a tangent line. So we have the slope, we have the point. So using the point slope form, we can guess the equation of tangent line. And then we can take the new points in terms of x-axis and then get the new points here. So these points in terms of coordinates we can calculate, and then take the difference. We have the dy here, right? We have the dy here, and now basically we are using dy to approximate delta y or vice versa. So we can compare how good is the approximation by looking at the different values. All right, so we also have we also want to look at the rate of change. So this is something we covered earlier. So again, we have the different quotients, and then by adding the limits, then we have the instantaneous rate of change, or the definition of the derivative. All right, so that's it for the first part, and thanks for watching. Hope to see you in the next part. Thank you.